Next up, let's talk about insertion sort. So insertion sort is another way to do sorting, and you might ask, why are there so many different ways to solve the problem of sorting a list? Well, sorting is super useful, so it ends up being a very well-studied problem. And in fact, we'll see better algorithms for sorting in a subsequent chapter once we've learned a little bit more about programming. But for now, the insertion sort algorithm works a lot like the bubble sort and the selection sort algorithm in that we take in an unsorted list of values and we return a sorted list of values. But whereas the selection sort was selecting items in sorted order and inserting them as it went, the insertion sort algorithm will take a random item, so the next item in our list, and insert it into the correct location in its output. So you can think of it as though you're working at a library and you have a stack of unsorted books that you need to put back on the shelf. You're just going to take the first one and then find the place on the shelf where it belongs, moving the other books out of the way so you can slide it in place. In practice, if we're doing this with a list of values, what we'll do is we'll take the next item from our list and we'll add it to the end of our sorted list, and then we'll swap it to the left until it's in place. Same sort of effect, just instead of finding the spot and shifting everything, we'll just shift it into its spot. The advantage of the insertion sort algorithm is that it's good for making very small changes to a nearly sorted list. Right? If our entire input is already sorted, then we're just going to be adding items to the end of the list. The items we're taking are just going into the output already in sorted order. We don't have to find anything. So you can think if you're running a web service that keeps things sorted like Spotify and some new music gets added, you just want to put that into a sorted list, you can add it to the end and do an insertion sort to get it into its place. So let's walk through how this works in practice. So again, our input is an unsorted list, and we'll have an output list that's empty so far. So to get the first item is pretty easy. We take the first item in our list, so the next value to sort is just the first item we see, and to put that in place in our output list, since it's already empty, it doesn't matter where we put it. So we'll just add that to the beginning of our list. The second item is just the second item in our input. Notice we're not finding any specific item, we're just taking the next one in order, and then we'll add that to our output. But now our output's not in sorted order, so we'll swap these until they are in sorted order. So these two items need to be swapped, so 4 is less than 7. The next item gets added into the end of our list again, and then gets swapped till it's in place as well. So 1 and 7 switch, and then 4 and 1 switch. And then we take the next item, swapping that until it's in place. Notice after one swap, that item's now already in its correct place. So once we see that 6 is greater than 4, which means 6 is also greater than everything that's in front of that 4 as well, because this is a sorted list. So once we've found the first item that's in order, we don't need to swap it anymore. We can stop moving this item and go on to the next pass. Next pass, we take a 5, put it at the end, swap it till it's in place. Then we take the 2, put it at the end, and swap it till it's in place. Once we've done this with all of the items, then our output list is the sorted version of our input list. In Python, we can create the insertion sort algorithm as we've created these other algorithms as well. So we start with our base code here, which has space to implement an insertion sort, has a function pre-built to generate a random list of numbers, and a main function for generating that unsorted list, sorting it, and then printing the result. So we need to implement the insertion sort algorithm. So in terms of design, we need to start with our input list and some blank output list. So say start with input and empty output list. So input is just a copy of our input list, and our output is just a blank list. Then we want to repeatedly take the first item from our input list, add it to the end of our output list, and then swap it to the left until it's in sorted order, or until it reaches the beginning of the output list. And we want to keep doing that until we have no more items to sort. So we'll say until the input list is empty. Then we'll repeat the following steps. We'll take the first item from the input. We will add it to the end of the output. Then we'll swap it left until it's in sorted order. Again, we're assuming increasing order, but it's very easy to just flip your conditions if you want to have decreasing order. Swap it till it's in order, and again, if we reach the end of the list, that's also considered the end of swapping to the left. And then once we're done, return the output. All right, so that's pretty easy to describe, so now let's see if we can't implement it. So start with the input and our empty output list. Now we're going to be using the pop operation again to remove items from our input list and put them into our output list. We're going to do a not in place sort here as well. So again, we'll start by taking our input list and copying it. So we'll say unsorted list equals unsorted list sliced from the beginning to the end. So shallow copy our input list, and then we'll make an output list. We'll call that the sorted list, and that starts just as an empty list. Now, until the input list is empty, so while the len of the unsorted list is greater than 0, so while there's still items in our input list, we're going to take the first item from the input list. So we'll say unsorted list dot pop. Again, we can say pop 0 or just pop blank. And that's going to return the item to us so we can use it. So I'll just call that item. And now if we have the current item in our hands and it's no longer in our input list, we want to add it to our output list. So we'll say sorted list dot append item. Now, appending to the end of our output list doesn't necessarily put it in sorted order, because we might have just taken the smallest item and now it has to shift all the way to the front of that output list. So the next step is to repeatedly compare and swap until our item is in sorted order. So what we need here is a nested loop. So there's probably a few ways we can solve this, but what we'll do here is we'll keep track of where the item is and shift it to the left over and over and over again until the item to the left of the current item is smaller than our current item. Right? If the thing to the left of me is bigger, then I'm not in sorted order. If the thing to the left of me is smaller, then everything to the left of that is smaller as well, which means I am bigger than everything to the left of me. So what we'll need to do is keep track of the current location of our item. So I'll say index equals the current spot, so that's the end of our list. So that's the length of the sorted list minus 1. Since we just appended this item to the end of our sorted list, it's at the end of that list, and the last index in that list is length minus 1. So now, so long as the item to my left is bigger than me, that means I'm not in sorted order. If I'm a 6 and there's a 7 to my left, then I need to swap with that 7. So while sorted list at index minus 1 is bigger than me, so sorted list at index, then we're going to keep swapping. This condition isn't done, we'll come back to it in a second. We also need to worry about hitting the edge of our entire list, but for now this gives us a place to start. So while the item to my left is bigger than me, we need to swap. So to do a swap in Python, there's a shorthand, or we can do the long form. I prefer the long form because once we move to Java for the next course, you won't have all these nice Python isms. So the long way to write this out is we create a temporary variable and we store one of the items in that temporary variable. So we'll say sorted list at index minus 1 goes into a temporary variable. And I'll take the item that I'm currently looking at and put it there. So sorted list at index minus 1 equals sorted list at index. And now I'll take the item from that temporary variable and put it to where I just cleared. So sorted list at index equals temp. And now the item that I'm looking at has just moved to the left one, so its index goes down by 1. So perhaps I'll describe these in comments here. So this is asking, while out of order, this says swap left, because index minus 1 is the item to my left. Those 3 lines say swap left, and then this one says update the current location. So it's going to keep doing that over and over and over again. Now what happens if we have the smallest item? So the item that we just picked up from our input list is the smallest item out of all of the items that we've seen so far. That means when I look to the left, that item's going to be bigger than me. I'm going to swap with it, and the next item will be bigger than me, and we'll swap with it, and eventually I'll get to the front of the list, and there won't be anything to my left. Now at that point, if I say sorted list at index minus 1, if index is 0, then that's not going to be the item we're looking for. That's going to be all the way to the right end of the list then. So before any of that, we'll make sure as well that the index we're currently looking at isn't the beginning of the list. So we'll say, well, index is greater than 0, and the item to my left is bigger than me. In that case, then we'll do these swaps. So once we've run through this loop, at the end of it, one of these 2 partial conditions will be false. So either the item's gone all the way to the left, or we've stopped a little bit sooner than that because we've found the item to my left isn't bigger than me. In either case, we're in sorted order, so we can stop swapping and move on to the next pass. So we go back up to the top, we take the next item, we add it to the end of the list, and we swap it left until it's in order. Once we've done that for all of the items, so once our sorted list is empty, then this whole loop is done. Our whole output then will be sorted because we'll have taken each item and swapped it through. So then we can just say return the sorted list. Save our code. And since main's already set up for us, we can just say Python insertion sort.py. And you can see we start with a random input and we get a sorted output. So in terms of correctness, this works just as well as the selection sort and the bubble sort did to sort a list of numbers. But what about efficiency? So in terms of efficiency, the insertion sort algorithm, let's say we want to sort through n total items, then for each item, we may have to compare it to all of the previous other items. Right? If we've taken the smallest item so far, then when we put it at the end of our output list, we have to compare it to all of the items before it reaches the front of our output list, at which point we've got it in sorted order. Now, upper bound, we can say for each item, the number of other items we have to compare it to is all of the other items, so n total items for each item. Now, in practice, that's not going to happen because for the first one, for example, we didn't have to do any comparisons. For the second one, we just have to do one comparison. For the third, maximum of 2 comparisons, etc., etc. But maximum, we have to consider n total items for each item. So if we want to sort n items, and for each one of those we have to do an upper bound of n comparisons, we say again we have a total of n times n, or order n squared comparisons total. Again, it's not exactly n squared, but it's of that magnitude. If our problem size goes up by a factor of 10, the insertion sort will take 100 times longer to run. Now the advantage of insertion sort versus, say, bubble sort or selection sort is that if our input is already almost sorted, then this algorithm will work very fast. So if there's few inversions, that is to say, if there's few items that are out of order locally, then we're not going to have to do a lot of swaps. We're just going to add the item to the end of the list and check the one next to it. It will be smaller since the sorted order is already in place. So then we just add to the end of the list and get the next one. Add it to the end of the list, get the next one. So without doing those swaps to the left, we're saving a lot of time. So if our input is already nearly sorted, this algorithm doesn't have to do nearly as much work as, say, the bubble sort in practice. However, when we're doing big O notation, we don't say in the best case, we say in the worst case. So in the worst case, we still say that's order n squared. Now, like I said, sorting is such an integral part of computer science that most languages already have some built-in facilities for managing sorting of lists. So in Python, for example, if we want to do sorting of a list, it's super easy. There's a built-in list method that takes a given list. You just say mylist.sort, and it will sort that list in place. So it doesn't return anything, it just mutates the list so that it's sorted in place. So if I have my list with a bunch of numbers, I can just say mylist.sort, and then it becomes a sorted list. When we use this built-in sorting method, it doesn't use any of the algorithms that we've learned so far in this class. It actually uses a proprietary sorting algorithm known as timsort, named after the person who created it, Tim. Timsort is a mix of the merge sort and insertion sort. So we haven't learned about merge sort, but we have seen insertion sort. The basic idea is when there's very large problems to solve, we can use this concept of merge sort, a technique we'll learn in a future chapter, to manage the big pieces of sorting. But then when we get close to having everything almost in order, then we can use the insertion sort to very quickly solve those smaller sorting problems in an efficient way. I should point out that the sorting algorithm works assuming that all of your inputs are sortable. So we've seen that lists can have multiple different kinds of values. If you have a list that's all numbers and you say mylist.sort, that will work fine. By default, we'll sort this in ascending order. But if you have a list that contains a string and some numbers and a Boolean in there, and you say mylist.sort, that will be an error because the algorithm can't find a way to sort the word false versus the number 4.5, for example. So the elements in your list have to be comparable in order for sorting algorithms to work, but this is true of any of the algorithms that we've covered today.